Let's look at some interest formulas. You've probably seen this formula before in college algebra or pre-calculus, and it's a compound interest formula. That is, the amount A is equal to the principal times the quantity 1 plus R divided by 100n raised to the nt power. And here are the definitions. That is, A is the amount, P is the principal or principal investment, T is duration in years, R is the annual percentage rate, and N is the number of compoundings per year. For instance, 12, 4, whatever type of setup you might be having. Now, of course, what this problem is addressing is allowing N to pass to infinity. And so you're thinking, okay, well, how can we utilize this formula to come up with a formula for continuous interest? If we call this compound interest, then the new formula would be one for continuous interest. So we're going to say that script A will be the limit of this formula as N tends to infinity. First off, we're just going to focus on the items that actually are functions of N or have N in them. So first we're going to factor the P, and then we're going to use the laws of exponents to move the T to the outside. So again, everything is nice and equivalent here, just using continuity and our properties about exponential powers. Now, in order to move this through, we definitely need to be able to use our definition of the natural base. So a way we can do that is to set H equal to the reciprocal of this term. That is, let H be 100N divided by R. And then if you solve for N is just RH divided by 100. So we can go ahead and replace this term with 1 over H. And then, of course, the H will remain inside, but the R over 100 will come out to join the T, again using the laws of exponents. So now we have a very familiar limit here. That is, the limit as H tends to infinity as of 1 plus 1 over H to the H power is just the natural base. And so we get P times the natural base raised to the RT divided by 100. So there's a formula for continuous interest. And of course, in this particular problem, we're writing R as a percentage, so we don't have the built-in decimal. So that's why we have the 100 there. Now, if we're interested in a doubling time, that is, how many years must pass before our principal investment doubles, we just replace script A with 2P, and the P's absorbed, and we get 2 equal to e to the RT divided by 100. Well, of course, a logarithm is the power of the base, so RT divided by 100 must be equal to the natural log of 2, and we can easily solve for T by multiplying by 100 over R. So we get T, which is the doubling time, will be 100 times the natural log of 2 divided by R. And of course, if R is equal to 6%, we can replace R with 6 and get 50 over 3 times the natural log of 2, which is approximately 11.55. So again, this really is a review of what you talked about in previous courses. Now we can actually extend this idea to the limit process that we learn in calculus, so maybe these formulas make a little bit more sense. And we are done.